Okay, class begins. Last time we have learned the Hamming distance. Hamming distance means the number of bit positions in which two code words differ is called the Hamming distance. If two code words are a Hamming distance d apart, it will require d single bit arrows to convert one code word into the other code words. So Hamming distance is the number of bit positions in which two code words differ. The error detecting and error correcting properties of a block code depend on its Hamming distance. So the concept of Hamming distance is important for determining how the detecting code or error correcting code designing. To reliably detect D errors, you need a distance D plus 1 code, because with such a code, there's no way that D single bit errors can change a valid code word into another valid code. When the receiver sees an illegal code word, it can tell that a transmission error has occurred. Similarly, to correct D errors, you need a distance 2D plus 1 code, because that way the legal code words are so far apart that even with D changes, original code word is still closer than any other code words. That is the principle of a Hamming distance. So we have given a simple example of an error correcting code. Consider a code with only 4 valid code words. These 4 code words. This code has a distance of 5 bit, which means that it can correct double errors and detect 4 bits error. If the code word, this one code word is 70 bit and appended by 3 1 bits arrives, and we expect only single or double bit errors, the receiver will know that the original must have been 50 bits and 51 bits. That is, we assumed that only a single or double bit error occurs. If there is no such expectation, then we have this result. Imagine that we want to design a code with M message bits and R check bits that will allow all single errors to be corrected. Each of the exponential 2M illegal bit messages has n illegal code words at a distance of 1 from it. Then each of the legal messages requires m plus 1 bit patterns dedicated to it. Since the total number of the bit patterns is 2n, the 2n. n bits. Each bit has two forms, 0 or 1. And we have n bits. So the total number of the bit patterns is 2 with the degree of n. So we must have this n equation. So using n equals m plus r. For example, and r. We have m bits, right? M bits. And r check bits. R check bits. And the total as n equal n is m plus r, right? So the total number of the bit patterns is the total number is 2n, right? 2n. Sorry. 2n, right? So this requirement becomes m plus r plus 1 less than or equal to r. For example, if m equals 4, if m equals 4, then what is the r? If m equals 4, then what is the r? So we have 4 plus r plus 1, right, equal less or equal than to 2 with the power of r. So r is and we should get the minimum integer value. So r is 3, right? 4 plus 3 plus 1 is 8, and 2, 3 is 8. So r is 3. So this is the example. We will not introduce the Hamming code in detail. Then we will talk about error detecting codes. Over fiber or high degree copper, the error rate is much lower. So the error correcting coding seems to be too heavy. So error detecting and retransmission is usually more efficient for dealing with the occasional error. We will examine 3 different error detecting codes. They are all linear systematic block codes: parity, checksum, and cyclic redundancy checks, CRC coding. First, the parity code. In a parity code, a single parity code bits is appended to the data. The parity bit is chosen so that the number of 1 bits in the code word is even or odd. Doing this is equivalent to computing the even parity bit as the modulo 2 sum or XOR calculation of the data bits. For example, when this bit stream is sent in even parity means there must be even number of 1 bit in this bit stream. The number of 1 bit should be even. So the meaning of even parity. So when this bit stream is sent in even parity, a bit is added to the end to make it like this. So with odd parity, then the bit stream to be transmitted becomes 10110101. The even parity, that means the bit transmitted, the bit stream transmitted, the number of the 1 bit should be even. So the number of 1 is 1, 2, 3, 4. That is even, right? Since it is even, so the bit appended should be 0. If we use odd parity code, it should be 1, 5 1 bit, 5 1 bit. This is the parity bit. So in advance, we should determine which code we will select, even parity or odd parity. A code with a single parity bit has distance of 2, since any single bit arrow produces a code word with the wrong parity. This means that it can detect a single bit arrow. Now we will talk about checksum. Checksum is the second code for arrow detecting. The checksum is based on a running sum of the data bits of message. It is usually placed at the end of the message as the complement of the sum function. This way, arrows may be detected by summing the entire received code word, both data bits and checksum. If the result comes out to be 0, then no arrow has been detected. For example, in the internet, a kind of checksum, 16-bit internet checksum used on the internet packets as part of the IP protocol. This checksum is a sum of the message bits divided into 16-bit words. Then we will talk about checksum coding in the chapter 5. So in this chapter, we will talk about CRC code in detail. The CRC code is also known as a polynomial code. Polynomial codes are based upon treating bit streams as representations of polynomials with coefficients of 0 and 1 only. A key bit frame is regarded as the coefficient list for a polynomial with key terms ranging from the term x key minus 1 to the term x0. Such a polynomial is said to be of degree key minus 1. And the high order means leftmost. The high order bit is the coefficient of x with the degree of key minus 1. Then the next bit is the coefficient of this term, and so on. For example, if we have this bit stream 110001 has 6 bits and thus represents a 6-term polynomial with coefficients 1, 1, 0, 0, 0, and 1. It's like this, right? So this one represents the coefficient of this term 1 represents this one. The coefficient of this term 1 represents this 1 bit. And this term, know this term. So the coefficient is 0, 0, 0. And the coefficient 1 represents this bit 1. So the bit stream is corresponding to the polynomial. When the polynomial code method is employed, the sender and the receiver must agree upon a generator polynomial gx in advance. Generator polynomial gx in advance. Both high and low order bits of the generator must be 1. That means this polynomial should be this form: 1 and 1 0 1 0 1 0 0 0 1 1 1, this form. And the lowest order bit must be 1. The first is 1, the last bit is 1. So the high and low order bit must be 1. So 1, 1, and 1. So the idea is to append a CRC to the end of the frame in such a way that the polynomial represented by the checksum frame is divisible by Gx. The idea is to append a CRC to the end of the frame in such a way that the polynomial represented by the checksummed frame is divisible by Gx. We will talk about the reason why the checksummed frame will be divisible by Gx. When the receiver gets the checksummed frame, it tries dividing it by Gx. The receiver, if the bit stream arrived at the receiver, then the receiver gets the checksummed frame, right? It tries dividing it by the generator polynomial, Gx. If there is a remainder, there has been a transmission error. If the remainder is 0, then there is no transmission error, or the transmission error cannot be found. So the algorithm for computing the CRC is as follows. We have 3 steps. Step 1, let R be the degree of Gx. Let R be the degree of Gx. For example, if the Gx is 1, 1, 0, 0, 1, if the Gx is 11001, then what is the R? What is the R? R is 4, right? If Gx equals 11001, then R is 4. That is this one. For example, if the degree is this bit stream, 110001, has 6 bits, but the R is 5, right? R is 5. This bit stream is 6 bits, then the R is 5. So append R0 bits to the no order end of the frame. So it now contains M plus R bits and corresponds to the polynomial X R times mx. Here mx is the message bit stream. Step 2, divide the bit stream corresponding to Gx into the bit stream corresponding to XR mx using the modular 2 division. Step 3, since we get the remainder on step 2, then we subtract the remainder from the bit stream corresponding to XR mx using modular 2 subtraction. The result is the checksum frame to be transmitted. Call this polynomial Tx. Then it should be clear that Tx is divisible by Gx. In fact, in any division problem, if you diminish the dividend by the remainder, what is left over is divisible by the divisor, right? So that is the principles of CRC. Let R be the degree and append R0 bits to the no order of the end of the frame. We get XR and X. Step 2, divide, then get the remainder. Step 3, subtract the remainder from the bit stream. Then we get Tx. It should be clear that Tx is divisible by Gx. So if we transmit Tx through network, then what the receiver received should be divisible by Gx. If it is not divisible by Gx, then there should be a transmission error. Then we should understand this equation. For example, step 1, we get XR MX, right? Append R0 bit to the MX, then we get the polynomial XR times MX. Then step 2, divided by Gx. So XR MX divided Gx, we can get Qx plus the remainder Rx. Right? So then if we subtraction or XOR Rx, then we get Tx. And we get Gx times Qx. Then Qx must be divisible by Gx because there's no remainder, right? If there is a transmission error, Ex, then it should be a remainder left. That is why the transmission error can be detected, right? For example, then we will illustrate an example. We assumed a frame 11010111 should to be transmitted using this generator polynomial Gx x4 plus x1 plus 1 plus 1 is x0, right? Then we get the frame, original frame, this one. The generator polynomial is 10011. Why it is the generator is 10011? Since the generator polynomial is x4 plus x plus 1, that is xgx equals x the coefficient times coefficient 1 times x4, right? Plus 0, coefficient is 0 times x3, right? Since there's no this kind of terms. 0 times x2, right? Times plus 1 times x1, right? Plus 1 x times 3, 0, right? So we can get 1 0 0 1 1, right? Can get 1 0 0 1 1. So the generator is 10011, right? So 10011. Then we will use the long division. Long division. We use the long division. Okay. The high order, the degree of the high order is 4. So the R is 4, right? R is 4. Then 4 0 bits should be appended at the end of the original frame. 4 0 bit, since the high order is 4, then R is 4, then 4 0 bit should be appended to the end of the original frame to be transmitted. Then we should use this divisor, then get a remainder. Then the remainder, the number of the bits of the remainder must be less than or equal 4 bits, R bits, right? So then we add 4 bits at the end of the original frame. So 0 0 1 0 appended here. So the transmitted frame should be this one. Then we will talk about how calculate So the procedure of the long division. Then there's 1. So we write 10011, right? Then 01, 0, 1, 0, subtraction 1 is the 1. No, we use XOR. We use XOR calculation. So if the 2 bits is different, we get 1. If the 2 bits are same, we get 0. If the same, get 0. If different, get 1. So 0, 1, different, we get 1. 1, 1, they are same, we get 0. 0, 0, same, we get 0. 1, 0, different, get 1. Then this 1, 1 is same, get 0. So we will not write 0 here. So the 1001. Then we write here 1 down to here. So 10011. Write 1 here and write the divisor 10011 here. So we get 3 zeros. They are same. 110, 110, 000, 000, 000. The 11, same, 0, not right. We are not write it. So we write the 1 here, write 1 here, right here. Then write 0 down to here. So 5 bits. 5 bits. So write 10011. 0, 1, they are different. Get 1. 1, 1, same, we get 0. 1, 0, different, get 1. 1, 0, different, get 1. So 1101. Then we write 0 down to here, down here. So the is 0, 1 different. So then at the last, we get this 0010. At 0, that is the procedure of the CRC calculation. It is some complex, but it is important. It is important for us to understand the CRC principles, and we will have some problems on the final examination paper. So we must understand very well about CRC calculation. We should grasp the method to calculate CRC remainder, to get the transmitted the frame to be transmitted. Then the power of the CRC is some limited. Some transmission errors cannot be transmitted at all. Then we will talk about the limitation of cyclic redundancy checks in next section. Let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Please keep connection. Please keep connection. We will talk about the limitations of CRC next section. Okay, let's continue. Then we will talk about the limitation of the CRC code. Now, the power of CRC code. Now, what kinds of errors will be detected? What kinds of code or what kinds of errors will be detected or will not be detected? Upon receiving the checksum frame, the receiver divides it by gx, by the generator polynomial gx. That is, it computes tx plus ex divided by gx. The remainder of tx divided by gx is 0. So the result of the computation is simply ex divided by gx. That is this one, right? This one. If there has been a single bit error, for example, ex can be expressed by x with the power I, where I determines which bit is in error. If gx contains 2 or more terms, it will never divide into ex. So all single bit errors will be detected, right? All single bit errors will be detected. But if the number of errors occurred is larger than 2, then there probably be some errors cannot be found. For example, if there have been 2 isolated single bit errors, we express the error bit stream is xi plus xj, where I is larger than j. So alternatively, this can be written as this one. So xj times xi minus j plus 1. If we assumed that gx is not divisible by x. A sufficient condition for all double arrows to be detected is that gx does not divide x key plus 1 for any key up to the maximum value of I minus j. Simple no degree polynomial that give protection to long frames are known. For example, this kind of polynomial will not divide x key plus 1 for any value of key below 32,768. So CRC is suitable to detect a single bit error. So this is extended knowledge points. Then we will talk about elementary design of data link protocols. We assume that the physical layer, data link layer, and network layer are independent processes that communicate by passing messages back and forth. A common implementation is shown in the figure 10. This is a physical layer, data link layer, network layer, and the upper layer. Then link layer, network layer, and application layer usually designed embedded in the operating system. Link network usually embedded in the operating system. And the link usually implemented as the driver program, driver coding. Driver is implemented in the data link layer. And the physical layer usually includes the implementation of network interface card. Network interface card, physical. And the underlying channel is the cable or physical media. And another key assumption is that machine A wants to send a long stream of data to machine B. For example, this is A, this is B, this is A, machine A, machine B, right? A, B, the key assumptions that machine A wants to send a long stream of data to machine B, long stream of data stream to machine B using a reliable connection-oriented service. We also assume that machines do not crash. We also assume that machines do not crash. So we assume the machine is reliable and robust. Then when the data link layer accepts a packet. When the data link layer accepts a packet, it encapsulates the packet in the frame by adding a data link header and a trailer to it. The frame is then transmitted to the data link layer on the other machine. We will assume that there exist suitable library procedures with the interface function to physical layer this interface function to stand a frame and use this kind of interface function from physical layer to receive a frame. Receive frame. This is a interface function. This is the interface function. Interface function. We assume that there exists a interface function as suitable library procedures to implement to send a frame or receive a frame. Okay. This figure shows some declarations in C program common to many of the procedures to be discussed later. 5 data structures are defined there. Boolean, sequence number, packet, frame kind, and frame, these variables. This figure gives some definitions needed in the protocol too. Then we zoom in. Sorry. Oh. Okay. This is some definition. This is a structure definition. This is some interface. And you can look this code in detail with the PDF file. Then we will illustrate a simple protocols named Utopian simplex protocol. As an initial example, we will consider a protocol that is as simple as it can be, because it does not worry about the possibility of anything going wrong. So this it is a simple. It is a simple, and don't deal with the deal with nothing wrong. It will not worry about the possibility of anything going wrong. So data are transmitted in one direction only. This assumption. Assumption 1. Data are transmitted in one direction, A to B. Both the transmitting and the receiving network layer are always ready. Both the transmitting and the receiving network layers are always ready. Processing time can be ignored and assumed that infinite buffer space is available. And best of all, the communication channel between the data link layers never damages and loses frames. This thoroughly unrealistic protocols, which we will nickname utopian, is simply to show the basic structure on which we will build the data link layer, data link protocol. So the utopian simplex protocols implementation is shown in this figure. So protocol 1 will define the event types and divide the sender one, the receiver one, and there is a while true, that means loop again and again. From network there, get a packet from network there, and put the packet into the buffer, and encapsulate the packet into a frame, and send this frame to the physical layer. So using this kind of interface. The receiver, what the receiver will do, while true, that means repeat again and again, wait for a frame to arrive, and receive a frame from the physical layer when the frame arrived, and get the packet from the frame and deliver the packet to the network layer. So that is the utopian. And you notice that this kind of utopian protocol is so simple that it does not deal with anything wrong. Will not deal with anything wrong. And we assumed there's no wrong. Nothing wrong. Assumed nothing wrong. So it is unrealistic protocols. So nicknamed with utopian. The utopian protocol is unrealistic because it does not handle either flow control or error control. Does not handle flow control or error correction. Its processing is close to that of an unacknowledged connectionless service that relies on higher layers to solve these problems. Though even an unacknowledged connectionless service would do some error detection. Then we will illustrate some improved version of protocols. A simplex stop and wait protocol for an error-free channel. Now we will tackle the problem of preventing the sender from flooding the receiver with frames faster than the receiver, right, is able to process them. The communication channel is still assumed to be error-free. So we assume that the physical channel is reliable. There's no errors occurred. However, the data traffic is still simplex from A to B. Simplex, unidirection from A to B. is a simplex A to B. So tackle the prevent the sender from flooding the receiver. So that means in this protocol, it will deal with, it will handle flow control, right? Via flow control to prevent the sender from flooding the receiver. So the general solution of this problem is to have the receiver provide feedback to the sender. Provide, that means the data flow, the data frames from A to B, transmit from A to B. And B should reply some acknowledgement to A. Acknowledgement, ACK, acknowledgement to A. So a general solution to this problem, the problem means flow control, right? This problem is to have the receiver provide the feedback to the sender. After having passed a packet to its network layer, the receiver sends a little dummy frame back to the sender, which in effect gives the sender's permission to transmit the next frame. The dummy frame means too short, even with no data in the payload, only header information in the frame. After having sent a frame, the sender is required by the protocol to bide its time until the little dummy frame arrives. This delay is a simple example of flow control protocol. The flow control protocol. Protocols in which the sender sends one frame and then waits for an acknowledgement before proceeding are called stop and wait. For example, we will write this A, the B at A, B, then A send a frame to B, then A stop, wait for an acknowledgement from B. Then B replied permission to A. Then A transmit the next frame. This is the first frame, then the second frame. So that is the principles of this stop and wait. Stop and wait, that means after machine A transmit the first frame, is stopped until received a reply from the receiver. So when received the reply from B, then machine A transmit the next frame. So this period is the waiting time. Okay. So this protocol is called stop and wait protocol. The code of the stop and wait protocol is illustrated here. Protocol 2, stop and wait, provides a one-directional flow of data from sender to receiver. The communication channel is once again assumed to be error-free. However, this time, the receiver has only a finite buffer capacity and a finite processing speed, so the protocol must explicitly prevent the sender from flooding the receiver with data faster than it can be handled. Then this is event type, means a packet or frame arrive. Sender to, this is a receiver, sender to, the receiver to, sender to, receiver to, sender to, receiver to. Then while true means process this segment again and again. Then from network layer means gets a packet from the network layer, or network layer delivered a packet to the data link layer, and encapsulate this packet into a frame, and delivered this frame to the physical layer, and stopped and wait for an acknowledgement from the receiver. Then what the receiver do? Receiver does wait for a frame arrive. If a frame arrive, then the data link layer will get a frame from the physical layer and process the frame and deliver this frame to the network layer and reply an acknowledgement to the sender. So this is two physical layer. This means send a dummy frame to awaken the sender. So it is this kind of code looks like a persuade code to illustrate the principles of the stop and wait protocol. An even improved version of stop and wait can be support noisy channel. That means the channel may be unreliable. So how to support noisy channel? Now let's consider the normal situation of the communication channel that makes errors. Frames may be either damaged or lost completely. However, we assume that if a frame is damaged in transit, the receiver hardware will detect this when it computes the checksum. When the acknowledgement frame gets lost completely, the data link layer on machine A eventually times out. So it depends on a timeout clock. So the duplicate frame also arrives intact at the data link layer on B, machine B, the receiver, to be able to distinguish a frame that is seen for the first time for the retransmission. The obvious way to achieve this is to have the sender put a sequence number. So the duplicate frame, how to find the duplicate, which one is duplicate frame. Then the sender should put a sequence number in the header of each frame it sends. Then the receiver can check the sequence number of each arriving frame to see if it is a new frame or a duplicate to be discarded. A 1-bit sequence number is therefore sufficient. So the sequence number should occupy 1 bit is enough. 1 bit is enough because the sequence number can be 0 or 1. That means 0 means this is a new frame. If the sequence number is 0, means this is a new frame. If the sequence number is 1, that this is a next frame. This is a next frame. Next frame. N-E-X-T, next frame. So the 0, the 1. So this example code of stop and wait protocol for noisy channel illustrated here. It looks some more complex than the two protocols, former two protocols. And now we will stop here, and then I will talk about something about experiment, because we will conduct the first experiment on March the 18th. March the 18th, on Friday, March 18th, we will conduct the first experiment, right? So on the first section in this term, we illustrate experiment arrangement, right? We will conduct 4 experiments. We will conduct 4 experiments. Then we will conduct the first one, packet capture and protocol analysis. 8 o'clock to 11:25 on March the 18th. And what kind of software we will use to conduct this experiment? We will use Wireshark. Wireshark is a powerful software to capture packets in the internet. And we can download Wireshark software with this hyperlink. And we will, I expect you download Wireshark in advance. Download Wireshark in advance. And installed in your local computer. And install the Wireshark, and I will illustrate Wireshark, the usage of Wireshark on Friday experiment. This is I will talk about experiment arrangement for experiment 1. Then we will have experiment 2 on April the 18th with the software packet tracer. And we can download the software with this hyperlink. So I also expect you to download the packet tracer in advance. There's the 2 versions. One is for Windows system, the other is for Mac system. And experiment 3, we will install and configure the network server on April the 29th. We can conduct the experiment on the platform of Windows or Linux system. Depend on your interest. Yeah, the experiment 4, design of communication software, we can design some communication program to make the 2 machines communicate with each other. And we will code some C programs with virtual C++ or GNU C or C++ on Linux system or on CYGWin platform. So we have 4 experiments. So on March 18th, I hope you can prepare something or and download this software. Okay, so much for today. And you can download the software Wireshark for the Friday, March 18th experiment. Okay, bye.